So yes, today I will start from a somehow different viewpoint. I usually start by uh, like motivating neurosymbolic. Now this is a neurosymbolic seminar. I think I should not motivate it. So we'll take a different angle for this presentation, but you will see the connections to neurosymbolic very soon. So this presentation is about a work that we will be presenting at NeurIPS later. I think it's in less than 1 month, which is like interpretable concept-based memory reasoning. But I wanted also to give a little bit more a broader perspective. So I will start from far and I will get there by the second part of the presentation. So this is a work done by my student David, and in collaboration with many Italian folks, so Pietro, Gabriele, Francesco, and Michelangelo. So I will start, and the setting in which we are is the one of explainable AI. So I don't have to convince any of you that artificial intelligence is really revolutionize everything that we do, how we live, how we work, how we interact, and it's nowadays in all kind of fields. It's in healthcare, it's in finances, autonomous driving. Yet there is still a critical question that we need to address, that all these systems that are entering our lives, we need to trust them, but how can we trust them if we don't understand how they work? And this is kind of like the mission of explainable AI, to make like these AI systems that are more transparent, that are interpretable and accountable for. And why is this important? Because in a sense, this is in many fields, like in medicine, in law, in security, this is not just a technical issue that we are facing. This is like a societal issue, an ethical issue. And so I like the field of explainable AI because it's a technical field that has really like societal impact. And when I started like my research career, that's what I wanted to do. I want to do technical stuff that have a huge impact. And I think that this field is an amazing field for this. However, nowadays, the field of explainable AI that is trying to explain this kind of big neural networks, these big transformers, it's not enough because it holds a lot of premise, but these explainable AI techniques, and I'm showing here one of the most classical one, the one of showing like a saliency map that explain a prediction. For example, here we have some oak, and we want to predict this. They give a prediction like with 99% accuracy, and they show some parts of the image that are very influential. But if this is an explanation, I would not trust this system. No, I have no idea what is going on within the system, because this is what the system like will tell us. An explainable AI model will tell us. I'm using these parts. How are you using them? No, and what these parts mean. I matter. And so this we can like highlight two main problems of these explainable AI techniques. One that is that explanations are usually post hoc, which means that they are generated after the model has already made the decision, and they are not really revealing how the model make the decision internally. They're giving some kind of surface level understanding, intuition, but that's not how the model make the prediction. And second, these explanations are low level. They're highlighting pixel in the sub-symbolic information in the image. So this is an eagle because of this and this pixel, which is very different for how human think and human reason. A human would have tell a similar explanation in terms, oh, this is an eagle because it's sharp yellow beak, a white head, and whatever. And so this is the need to shift from the perspective of explainable artificial intelligence to the perspective of interpretable artificial intelligence, where we want to go from this post hoc interpretation of a black box model to a new class of models that are inherently understandable. So in a sense, we want to make models that are transparent, interpretable, and accountable by design. And so we want really to move from explaining what a model did to understanding how really the model thinks. And I want to start from one of these models, or a class of these models, and to like motivate what we propose in this paper. So these models are called, this class of models are called concept bottleneck models, and are interpretable models that are made by starting from a deep learning model. You can think of it of any neural network, and add to this neural network human understandable concepts. So let me just give show a schematical description. So here in the image now you see some fruit, an image of a fruit as input, and the task here is to predict whether this fruit is an apple or not. It's just like a toy example here. So if you would ask to a neural network or any deep model to solve this task, then this image will get processed and projected into intermediate representation. And finally, in the last layer, you will predict either a probability or a score that will tell like how confident the model is for this to being an apple or not. Like in concept-based models, you instead do the same prediction, but in a two-step process. First, you will map your image to a set of human understandable concepts. So here, this image will be mapped to like the concept red, that is true, soft, that is false, and round, that is true. Meaning like that the object that is represented in the image is a red, not soft and round object. And then a second neural network will just take this concept and make the final prediction. And why this is a more interpretable model? Because now every time the model says this is an apple, it can always trace back its decision in terms of this high-level concept. Say, okay, this is an apple because I think it's a red object, it is not soft, and it's round. And this is very different from the explanation that we've seen before. This is not a post hoc explanation. This is actually an intermediate representation that the model processed while doing its prediction. However, by doing this, there are like strong and important shortcomings of this solution. And so that CBMs are only the starting points towards like real interpretable models. And the first shortcoming is that by forcing the model to make a decision only based on this concept, actually you are compressing the representation of the model. So the capacity of the model here is compressed, and this is the idea of a bottleneck. Now, the concept form a bottleneck in the representation power of the network, and this can result, and usually does result, into like lower accuracy models. Because in a sense here, if the model needs more information than the concept that are still in the input but are not represented in the concept, then it will fail in making a right prediction. Moreover, there is also interpretability problem here, because while this model highlights some parts of the decision process, and in particular the concepts that are used for the decision-making progress, actually the process of taking the decision is still a black box model. We are still using a neural network, so we don't know how these concepts are used. Is it the red concept that is like contributing most to the prediction, or the sound, or a combination of this? So here, these models are still like just more a paradigm that really a final solution to the interpretability problem. And right now, the models that people use in mostly are originates from this CBM, but usually they have this kind of side paths. So they like improve again the representation of the overall model by adding some extra capacity, some like information that should not pass through the bottleneck. And the research now is that, okay, how can we design this intermediate representation that is both human understandable from the concept side and like latent in the neural side? How can we design this representation, for example, in terms of disentangling the representation, like not duplicating the representation in both the path And of course, you can regain a bit the accuracy of the original plain neural network, but these solutions are even worse in terms of interpretability, because who knows what's getting coded in this latent representation. And so this is the point where we try to make a contribution, and is that we can define the contribution in terms of two questions. First, we want to know whether we can still exploit this side path, since this seems to be fundamental to have high accuracy model that do not incur into the bottleneck problem. So can we design still a side path that, however, does not harm the interpretability? And second is, can we also have an interpretable decision making? Can we avoid to rely on neural network to take the decision? And this is what we are labeling the solution to these problems, what we are labeling nowadays as this neural interpretable reasoning paradigm. And let me dig into it. So let's go a little bit more into detail what actually we did to answer these two questions. So in a concept bottleneck model, no, this is just I'm exploring the image before and expanding it, and there are actually two neural processes, no? Both the prediction of the concept and the prediction of the downstream task are two neural processes. What actually is buying has the interpretability is this intermediate representation that is both symbolic, so it's made of symbols that are human aligned. These are very important feature of concept-based model, that usually these models can be trained end-to-end, but usually exploit also additional supervision of the concept. And this additional supervision has to be seen as a way of aligning the semantic of this concept to the human. So we want that when the model predicts red, it's exactly the same red that we think is not just some other kind of activation in the network. So in a sense, the interpretability comes from picking one part of the original model, one intermediate layer, of the network, and making it symbolic and aligning it to the human understanding. So we asked ourselves, can we do the same for the decision-making progress, not from our representation? Can we use a similar idea, but for the decision-making progress? So for the second part of this model, which is now just a neural network. And this is what we did. We are still a concept-based model, so we have still this process of neurally predicting the concept, but we replicate this also for the decision-making. And in practice, what we do, we add a parallel layer, a side path indeed, that is again symbolic and aligned with the human. And in particular for us, this is a rule generation process. So we use another neural network that generates the rule that needs to be used to make the final decision. So now we have these two parallel paths that are very similar in structure. They are making a prediction of a symbolic component that is human aligned, but one is representing the concept and one is representing the decision-making process that we want to use our concepts to predict the final task. And then you can see that actually making taking the final decision can be completely encoded in a symbolic execution. Because we have a rule now. For example, we are saying, oh, well, if we want to predict an apple, we have to check whether the object is not soft and it's round. So we can just pick this rule, evaluate this rule on the concept, and make the final prediction that, for example, in this case, the image in an input is an apple. So if we look, this is not really an architecture, it's more like this schema, this paradigm. We have, again, a concept-based model. So we have still a symbolic human-aligned representation layer, which is very good for interpretability. We have a symbolic human-aligned decision layer. That is, again, is good for interpretability. But differently from concept-based model, this decision-making is not like a process that starts from the concepts and goes into the task, but it starts directly from the input. So actually, since this decision-making process is neurally generated, these models are can be very accurate, so they do not incur into the bottleneck. So one nice way of looking at this paradigm is in a, let's say, neuro-symbolic way or logic way, because what is happening here is that we have this architecture where the upper path is actually predicting the atomic facts of the reasoning. So that states what is the content of the image. For example, here is saying this image is representing a red, not soft, and round objects. So this would be the neural predicates in terms of neuro-symbolic AI, what people call neural predicates. But then we have the same idea, but for the rules of this logical language. So we are saying, look, if the object is not soft and it's round, then it's an apple. And so these are kind of neural rules again, and then actually the taking the decision can be mapped to any kind of logical inference. Therefore, since these facts and this rule, then the object is an apple. So you can map it to any kind of Turing proving, for example, some kind of modus ponens. So right now, what I've showed you is more like a high-level overview, but we are still want to design models. We want these models to be mappable and implementable in deep learning frameworks. So we want kind of computational graphs that are end-to-end differentiable. So let's dig a little bit into how can we start from this schema and get an actual model. So one important, so maybe to start, the concepts are very common in the concept based field. They are represented like as a Boolean variable. So you can say, okay, we have the concept rate that is a Boolean variable, so it can take either 1 or 0, true or false. And you can have, so you have a truth value for each of the possible concepts in your vocabulary. But how to represent rules? Now, because here we have a neural network whose output should be a rule. What we do is something that is very simple. Probably there are other ways, but this seems very easy to implement. Is just to kind of replicate what we did for the concepts. So we again make a prediction for each of the possible concepts, but now the meaning of this, so we don't predict just one value for each concept, but we predict 3 values, which we call the roles that the concept have for making for a particular task. So we have one of these rule for each of the tasks. For example, here you have to give for given that this is for the task apple, so predicting whether it is an apple. So here for each concepts, we make a 3 prediction that are representing the role of this concept in making the prediction of the task. So what is the role of red in making the prediction apple? So what these 3 roles are very simple. They are either I means irrelevant, so it means red is irrelevant for predicting apple, are negative, which means that soft contributes with a negative polarity to apple. So you want things that are not soft in order to be apples. And in the last case, you have positive polarity. So you say, okay, something is an apple if this round positive. No? And so once you have this kind of representation, and remembering that every time you do this prediction, you do this for all tasks, so the task is given here, you can like map this into this kind of implication rule or inference rule. Not soft and round, then apple. And why this is a nice representation? Because then we can map the symbolic execution again into a logical formula. I don't want to go into the detail, but actually if you have this representation, so you call this like the concept Ci means the value of the concept I. So if I is red, Ci is like C red is 1, or and C soft is 0, and so on and so forth. And like here, Ri is the role of concept I. So for example, Ri of red is I, it's irrelevant. So if you can represent these variables here, then this symbolic execution, so making this kind of logical inference, can actually be encoded just as evaluating this formula. And this formula tells simply that for all your concepts, the task y, it's true, either if the role of that concept is irrelevant, so you don't actually either check its truth value, or if the role is positive, then the concept must have a positive value, and if the role is negative, then the concept must have a negative value. So in a sense, you're saying every time you predict a role positive, then you expect the concept to be positive, and every time you predict the role to be negative, then you expect the concept to be negative if you want to make the prediction from this task. Okay, so you have maybe now a vague idea about how this architecture can look like, but again, this is a symbolic architecture, and we say that we want something that is end-to-end differentiable. So as we always do in our lab, then we use probabilistic semantics for this logic. So what we need to do now is, both for the concepts and the rules, we need to give a probability distribution. And I also want to tell you again that you see that in all the description, there is this kind of symmetry. Whatever we do for concept, we do with rules. The differences are very tiny and technical, but we are keeping this kind of symmetry. So for the concept, we do what people do every day in Neuro-symbolic. Every concept is an independent Bernoulli distribution. So it's representing a binary random variable that is neurally parameterized. So what does it mean is that we have a neural network for each concept, so Fi, that takes the image as input with some parameters, and provide as output for every concept what is the probability for that concept to be true. These are, like in probabilistic logics, are the probabilistic facts. And instead, for the roles of the concept in a rule, we use a categorical distribution over the three values p, n, and I. So here again, you have a neural network that takes the image as input and output three possible scores. So you can think that there is a kind of softmax activation that is telling the probability for each concept and each task to be positive, negative, or irrelevant. And once we have this probability distribution, then actually the probability distribution over the task can be simply obtained by evaluating like the probability that this formula holds. So actually, this is like just homeworks, but it's super easy to show. Maybe a property, this is very efficient. This is like linear in the number of concepts, this computation. So it's not that that computationally complex. And actually, this idea was already in a paper that we published last year at ICML, with the disclaimer that back then we were using a fuzzy logic in interpretation, but nowadays we have shifted to probabilistic semantics, but the general idea still holds. And what we showed is that these reasoners that we get are actually trying to, like successfully find a better trade-off between interpretability and accuracy. So here we had like five tasks, 5 different data sets. They are all classification. Right now we are only doing some classification tasks. So you can think that from left to right, these tasks are more and more complex. So the first 3 are actually some like artificial tasks that we designed in order for the concept to be more and more of a bottleneck. And while these 2 are 2 standard datasets, this is like in like a molecule generation, molecule classification, and this like some classification of images of faces. And actually, in the x-axis of these graphs, you see 2 sets of models. On the left, like in solid colors, you have models that are interpretable. And here we meant by interpretable models that have both a concept layer and an interpretable prediction. So we have our model, which is the blue one, and also some like simple concept-based models that substitute the last neural network, so the task prediction, with some interpretable models, so either a linear layer or a decision tree. And while on the right here, in like these dashed colors, you have models that are not interpretable. So these are the models that use that side path I was telling you at the beginning, in different variants here based on the kind of task predictor that you use. But what it's interesting to see here is that while like increasing the complexity of the models, our model, which is the blue line here, is the only one that between the interpretable models that keep an accuracy that is on par with the non-interpretable models. And actually, for example, here in Celebre, it's also a little bit better within the variants of the other models, but because in general, this concept also imposes some kind of regularization effect. So you can have this kind of results, but in general here, the point is that you are not losing accuracy and you are not losing interpretability with this kind of models. And moreover, since we are neuro-symbolic people, we wanted to have some comparison with other neuro-symbolic models. So we picked the famous MNIST edition dataset, and we tried our model, but without any rule. We could show that actually our model could recover the ground truth rules, and in terms of accuracy, it was almost on par with the other models by differences very few, like less than a point. In particular, in this dataset, actually, we're not even using the supervision of the concepts, just to make a fair comparison. So that's nice. However, there is still a disadvantage of this approach, because the kind of interpretability that it provides you is what people in explainable AI call local interpretability, which means that these models are interpretable only when a specific instance is provided as input. So for example, here you have this Apple image as input, and only when this image is presented to the system, then you can understand what the model is doing, for example, for taking its decision. But if you were to ask the model, okay, which kind of rules can you use on all the possible images, then there is no way that these kind of models will help you in any way. And that's the issue that we were trying to solve in this NeurIPS paper of this year. And actually, we started from this previous model. I will show you in a second how. And we actually showed in a workshop paper that there is a nice connection, as one being an approximation of the other, that I will not dive into the details. If you are interested, I can explain you later. So what we do is to start from this same model, which provided local interpretability. And what we did is to change this neural rule generation in what we called neural rule selection. So actually, the idea is that the model overall, the pipeline overall, it's exactly the same. We still want some kind of module that has some neural spice in it to generate a rule. But the way this happens is different. And actually, in these details, we can move from local to global interpretability. So let's give you some details about it. How this generation works is in 2 steps. We actually have 2 components here. We have a neural selector and what we call embedded rule memory. So this embedded rule memory, you can think it's a list of embeddings, like a matrix where each row, it's a different embedding. And now the idea is that this neural selector will select one of these embeddings from this memory, and then the selected embedding gets decoded by a neural network, which output is exactly the same categorical softmax we have before for the rows to create the rule. So actually, the only difference of this model is in this interaction between a selection mechanism and a differentiable memory. So in a sense, you can also simplify this scheme in like a neural selector that selects from a set of learnable rules. And why this is nice? Because you see here that the input image only goes as input to the selector, but not as input to the rules. What does it mean is that at the end of your training, when you have your trained model, and so when these embeddings have been trained at convergence, you can stop your model, you can pick all the rows of these metrics, and you can decode them. And you will have all the rules that the model can use at inference time on any input, both in distribution and out of distribution. So the model will never use a rule that is not in that memory. So you set the number of rules that you want, 10, 20, 100, 1,000, whatever, but then the model will only use at most those rules and exactly those rules, which means that we can give a logical interpretation of actually of what this selector can do. So no matter what the rule is selected, this is the rule that the model can use. And again, the details are not important, but this is exactly what we had before. It's like the prediction once a rule is already been selected, and now this is like a disjunction, because you say one of these rules should be selected. So you have here a disjunction over all the possible selected rules. So this is a logical rule, and you know that the prediction that your model will make is exactly equivalent to this rule, and this rule can be verified. This is a logical rule, so you can pick this rule, you can use your favorite like formal verification rule, either for example model checking. We like our theorem provers because that we can implement in logic programs, but that will not change the stuff. So this model is verifiable. You can ask questions about what will model will and will not do. But then you may think, okay, but is this restricting somehow the capacity? Because we came to here in order to have models that still have this kind of side paths that allows them to be very accurate. And actually the answer is no. What we proved in the paper is that this architecture, we call them concept memory reasoners, are universally binary classifiers. So actually you are not losing any kind of representation power. The only thing is that you need to have at least 3 rules, because what we proved is that with 3 specific rules, you can actually make any kind of binary classifier. So we tried this model. Of course, we did the same accuracy experiments of the previous paper because we have to, and we show that we are not losing any accuracy with respect to the previous models, but we showed that now we can actually formally verify our system. Of course, we didn't go too much into the detail. These are really fundamental kind of paper. But for example, we had one task that is the MNIST addition again, but we modeled the digits of this MNIST addition task, not in a mutually exclusive way. So actually an image of, I don't know, a digit could be at the same time a 0 and a 1. But then what we try to check is whether actually the fact that the model can represent a digit both as a 0 or 1 is used in the decision-making progress, and we could verify that actually our model was not using this representation power. So every time a prediction was made, only one digit per image was used. And moreover, in Celebi, we tried some kind of verify some consistency rules. So in the way we design the task in Celebi, you have faces of people with some attributes, like if they have some kind of makeup, they are bald, the color of the hair, and we pick some of these concepts and we put them as task, and we wanted to see whether we can predict this special concept from the other concepts. So here we had, for example, bald, that was one of the concepts, and wavy hair, which was the task. And we actually checked, we could formally verify that our model would never make a positive prediction for bald and a positive prediction for wavy air, which it's nice because you can verify that your model is not doing things that are disaligned with the human. But we also verified that by doing this, we were not actually losing accuracy, and that this kind of nice universal approximators theorem actually was also giving experimental evidence. So what we try to do is to start with cell Bay again. So you have to read this graph from the right to the left. It's easier. So on the right, you have the standard task, which is made of 37 concepts. What we try to do is to retrain the model with a decreasing amount of concept. The idea here is that suppose that the user, the designer of the model, don't know all the concepts, only provide some of the concepts that he thinks are interesting for the task at hand. Then, of course, the less these concepts are, the stricter the bottleneck is. So standard bottleneck models, which are this red and gray curve here, you see here, they completely drop in accuracy, of course, when you provide less and less concept, while our model, together with some other black box models, keep its accuracy very, very stable. And this is due to this universally approximator. Of course, actually, you can see here a nice property. So our model is the purple line here in the graph. And you see that actually when it has more concept, it's actually a little bit less performant than the black box model, because intuitively what our training objective is doing is to force the model to use the concept as much as possible, because of course we want like meaningful explanation. If we don't have enough concept, then what can you expect for explanation? You are not giving the model any kind of language to provide you explanations. So actually the more concept, the more effort our method will make in giving you interpretable predictions, and that's the reason for this. While when you don't give concept, then it's just like a black box model. And our model is still a concept-based model, so it also enjoys all the nice properties of CBMs. One of these is the idea that in CBMs you can perform interventions on the concept. Interventions of the concept means that at test time, the user can fix one of the prediction of the model, and by doing this, you expect that the task will be adapted to and will respond to this kind of interventions, and hopefully it will respond in a way that is like aligned to the way the user would think. So suppose here that we have this kind of cactus as an image, and we have two concepts, again, very trivial, stupid, just task for example, and you have like two concepts, whether the cactus is healthy or is dying. It's just one concept, one is the opposite of the other. And suppose that we are saying, okay, the concept, the cactus is dying, and then the task is to predict whether to water or not. And so when the concept was yes, it's dying, then the water is yes, you have to water it because it's dying. But suppose that the user say, oh, this cactus is like this for an age, it never died. So you say, oh, look, it's not dying. Then you expect your model to change the prediction accordingly. So then if it's not dying, there is no need to water it or something like this. So in this way, this is a tool that CBM provides to the user to interact with the model and check whether the task prediction is aligned to our understanding of the model. And of the prediction task. And we did this as well. So this was the MNIST addition, where on the validation set we have this 97% accuracy. But then after testing the model, we use the concept annotations to fix the wrong predictions. So every time the model make a wrong prediction of the concept, we were fixing it exactly like here. And as a result, the task prediction had 100%, which means that actually the task prediction, so the rules that the model has learned, were perfect. The problem was in the prediction of the concept, which usually concept-based models do not deal with. You want to be interpretable from the concept onwards, because you want to be interpretable at the level of the human understandable concepts. But again, as I showed you a couple of times, in our model, there is a complete symmetry between the concept and the rules. So our model allows a new way of doing interventions, which is a rule intervention, because now we have this nice memory of our rules and we can start playing with it. So we tried a very simple experiment here. We limited the amount of rules that the memory can use a lot. So actually the task could not be solved with enough rules. And our model, when this happens, it starts to merge rules together to still have a very good good prediction. But of course, the rules start to be less useful. And what we did here, and for us, this was just a way to mimic a way in which the model is in a not very nice optimization solution. And what we did is to act one ground truth rule in the memory, and as an effect of that, all the other rules gets fixed. So in this idea that you can intervene on the rules at a certain stage of the training, should not be at the end, could be during the training, with some additional information, maybe in the zone, like the predictions where the model is making the most mistakes. And by effect of this in a kind of active learning framework, you can fix and guide the learning of the rules as well. But the nice property here is that now the user can not only interact with the concept, which is like the standard in CBNs, but can also interact with the decision-making process, either to understand it, modifying it, and tune it. So that was it. I gave you this kind of high-level overview of what we try to do with this neural-interpretable reasoning strategy. And I've tried to convince you that these models are accurate. This is due to this nice selection mechanism together with end-to-end rule learning. Are interpretable because they are both concept-based and rules and based on rules. So we have this both the representation layer and the decision-making layer are both symbolic and human aligned. And finally, there are some nice properties of these models. We can describe it using our probabilistic semantic. The linear, like the likelihood can be computed in linear time, and it gives you all these nice properties of CBNs, of interact with the model, and in particular, they are globally verifiable, so you can verify your model after training and before deploying it in the real world. So that was my last slide. I hope I am in time. I didn't have a reference for time, but I hope that's okay.
Perfectly on time. Okay. So thank you very much. Thank you. So let me just stop the record.